Okay, this is a really good question. Basically, what this comes down to is what is the difference between sample standard deviation, S, and population standard deviation, sigma, and how are these calculated differently? Okay, so this first table is showing how to calculate sample standard deviation, S. And in this example, we have data. So we've actually measured the diameter of rose blossoms. Looks like we have 1, 2, 3, 4, 5, 6 of them. Okay, so we have these observations, and then from each observation, we find how different is that observation from the mean, right? So that's x minus x bar. And then we square that difference. Basically, squaring the difference is kind of getting rid of this negative sign, so we don't care. So if here's the mean at 6, this observation 2 was 4 less than 6. An observation 10 was 4 more than 6. So notice 10 is 4 more than 6. 2 is 4 less than 6. But when we're calculating standard deviation, really we don't care about is it below or away or above the mean. What we care about is how far away is the observation from the mean. What is the spread of the data? So that's basically why we square. We square so that we can get rid of the sign. Okay, so notice these both have the same square. 4 squared and negative 4 squared are both 16. All right, then we basically take an average of those square differences. So we sum them all up. We get 70 is our sum. Okay, now how do you find an average? You take the sum and then you divide it by the sample size, right? So the equation for S is the sum of x minus x bar squared. So the sum of all of those differences divided by the sample size. And then lastly, we take the square root to basically undo the square, right? So in this example, if you were to find S, you would finish this problem by saying, okay, well, S equals the sum, which is 70. The sample size is 6. Oh, that's right. We also have a term that makes this basically non-bias. So this is minus 1. Sorry. So it's n minus 1 instead of n. And it's basically an average. You can think of it as an average, but this minus 1 makes this this estimate of sample standard deviation a non-biased estimator, which means that it does a better job of approximating the population standard deviation. Okay, so there's kind of a nuanced detail there, and we don't get into it into an introductory statistics course. If you go up and learn more about statistics, they'll talk about why that is minus 1. But here we just go ahead and accept that's minus 1. Okay, and then take the square root. So this is the square root of 70 over 5. Okay, so and that is the square root of 14, which comes down to 3.74, right? So on average, these observations are differing from the mean 3.74 units or inches, okay? All right, so that's how to calculate the sample standard deviation. Now, what if you don't collect a sample, but you do know something about the population? So that's what's going on over here. Let me scroll up. So when you're finding the population standard deviation, sigma, we do not collect a sample, right? We have not collected a sample, but we know something about the population. If we read through this this example here, the number of time buyers saw infomercials. So someone saw an infomercial once, 27% of the time. They saw it twice, 31% of the time, right? And this is not, we have not collected data. If we collected data, what would that data look like? It would probably be, say we were to collect 100 data points, we would have 27 ones, 31 twos, not exactly because it's random, if you were to collect a random sample, you would have, approximately 27 ones, 31 twos, 18 threes, 9 fours, and 15 fives. Okay, so it looks like 4 is the least number, least likely that you would have someone who would see an infomercial 4 times, right? So what's important to take away here is that this is not a sample. This is a description of what's going on in the population. Okay, so when we calculate our population mean, we do it differently. Okay, how do we do it? Well, X is still the number of viewings. So 1, 2, 3, those are the different possible values X can take. Okay, though this isn't saying that we saw one person that saw 1 infomercial, one person that saw 2 infomercial, one person that saw 3 infomercial, one person that saw 4, and one person that saw 5. That's not what this is saying. Rather, this is the possible values, the possible number of infomercials they could have seen, and then P is the probability of having seen those number of infomercials. Okay, so what is X times P? This is basically becomes like a weighted mean, right? So sample mean, X bar, is the sum of the data divided by the sample size. So basically every observation is getting an equal weight, right? So every observation, you could think of this if you were to, calculate the sum of 1 over n times x. So basically, if I had 6 observations, I multiplied every observation by 1 over 6 and multiplied that by by x, and then sum them all up. That's the same thing as summing and then doing the division. So every observation is having the same weight. The weight is just 1 over the sample size. Well, now here, the weight is the probability of having of seeing that observation, right? Because, like, for example, number 4, it's very unlikely we'll see a number 4. Okay, it's the least likely that we'll see a number 4, so it should be weighted less. Okay, so anyway, we take X times the probability of seeing X, and we get these numbers here. So 0.27 is 1 times 0.27. 0.62 is 2 times 0.31. 0.54 is 3 times 0.18, etc. Okay, so then that's how you find the population mean mu, right? So this is population mean mu, not sample mean X bar. Okay, so you sum them all up, and then you get this number here. So then once you have the population mean, you need to do the same thing where you basically find the difference between the observation and the population mean. So this number here, negative 1.54, is 1 minus the population mean, 2.54. Okay, this is negative 1.54. Okay, the next one is 2 minus, because it's the 2, right? So you take X and then you minus off mean. So 2 minus 2.54 is negative 0.54, okay, etc. All right, then next, what is this one here? This guy is the square, right? So if I were to take negative 1.54 and square it, I'll get this guy, okay? So if I take negative 0.54 and square it, I'll get this guy here, 0.292. All right, then lastly, I need to multiply that square by the probability of observing that observation. Basically, I need to weight it, right? So let me use a different color here. So what I'm going to do is I'm going to take this number and I'm going to multiply it by the probability of X. So 2.372 times 0.27 is 0.640. Okay, again, 0.292 times 0.31 is 0.091. Okay, etc. Continue doing those calculations, then sum them all up. All right. That sum is the variance. It's sigma squared. So to find the standard deviation, the sample standard deviation, the only thing that you need to do is take the square root of that number. Okay. So take the square root of the sum, the square root of 1.869. Okay, take the square root, and then you get your answer. This is the population standard deviation. Right. I hope that clears things up. If not, please let me know any follow-up questions that you may have.